increased volcanic activity, the latest eruption of Mount Etna, and its scientific impacts. Introduction: the ongoing dynamism of Etna. Mount Etna, located on the eastern coast of Sicily, Italy, is one of the most active volcanoes in the world and the largest in Europe. Its eruptive history spans at least 2.7 km, and studies show nearly continuous activity over the past decade. Late December 2025, seismic monitoring systems began to record increases in volcanic tremors, ground deformation, and gas emissions signals volcanologists interpret as precursors to eruptive episodes. By the 24th of December 2025, these geophysical indicators culminated in renewed eruptive activity from multiple summit craters, particularly the northeast crater. Geological characteristics of the 2025 to 2026 eruption. Eruption style and mechanisms. The eruption exhibited characteristics typical of strombolian activity, marked by intermittent explosions that eject lava bombs, gas, and pyroclastic fragments at varying intensities. Key geological processes included crater collapse. Part of the southeast crater structure collapsed, triggering pyroclastic flows and a towering eruption column several kilometers into the atmosphere. Lava fountaining. Persistent fountains erupted from summit vents, contributing to the dynamic, multi-phase nature of the event. Gas and ash release. High concentrations of sulfur dioxide and ash were injected into the troposphere, detectable via satellite instruments. These eruption styles reflect magma ascent and degassing behavior influenced by Etna's complex plumbing system, a basaltic magmatic regime characterized by frequent pressure fluctuations, leading to episodic explosive behavior. Monitoring and scientific observation. Volcanic monitoring techniques. Continuous monitoring by the Istituto Nazionale di Geofisica e Volcanologia (INGV) provided real-time insight into activity levels via seismic networks, recording tremor spikes as magma moved upward. Ground deformation measurements. Long-term deformation records indicate magma chamber inflation driven by influx of unerupted magma phenomenon quantified in multi-decadal studies showing Etna's volume increasing by millions of cubic meters annually. Satellite remote sensing, detection of soap plumes, and ash distribution via Copernicus and other Earth observation platforms. These data streams enable volcanologists to differentiate between transient outgassing and sustained eruptive escalation, crucial for hazard forecasting. Environmental and atmospheric impacts. Local effects. The injection of ash and volcanic gases into the lower atmosphere affected regional air quality. Dense ash columns have been observed rising up to approximately 6.4 kilometers above sea level at peak activity, with plume dispersal influenced by wind patterns. Ashfall can reduce air quality and visibility, posing respiratory risks, affect agriculture through ash deposition on crops. Disrupt local infrastructure and transportation. Broader atmospheric interactions. Volcanic eruptions can influence atmospheric chemistry and even disrupt layers far above the surface. Research from a 2015 Etna eruption showed that significant volcanic energy perturbed the ionosphere hundreds of kilometers above the volcano, a reminder that eruptions can have vertically extensive effects. Societal and economic impact. Tourism and local economy. The eruption sparked new safety restrictions in Sicily, with authorities limiting access to volcanic vents and lava flows to protect visitors and residents. Tour guides protested these limitations, highlighting the tension between public safety and local economic interests tied to tourism. Aviation and transport considerations. Ash clouds led to aviation alerts in past eruptive episodes and have the potential to affect flight operations due to ash ingestion. Hazards for aircraft engines. Scientific importance and future research directions. Mount Etna remains an invaluable natural laboratory for volcanic science. Hazard assessment. Its frequent activity provides continuous real-time data to refine eruption forecasting models. Magma dynamics. Ongoing studies of ground deformation and gas emissions contribute to understanding how magma bodies evolve and migrate. Atmosphere-volcano coupling. Observations of high-altitude disturbances point to interactions between surface eruptions and atmospheric layers. Future research will benefit from integrating multidisciplinary datasets including seismic, geodetic, remote sensing, and atmospheric chemistry to improve predictive capabilities and risk mitigation strategies.